Hello, mathematicians. Today we're going to be doing lesson 1, 2, and 1, 3, just talking about points, lines, planes, and line segments. As usual, we'll start with the warm-up problems over here. Since this is really toward the beginning of class, we're going to just start with some basic evaluation of expressions. Here's an example on the far left over here if you want to take a second to look at that and try to remember how to do this stuff. Just remember PEMDAS, right? Remember that from your previous math classes. That would be please excuse my dear Aunt Sally, meaning that parentheses come first, followed by exponents, followed by multiplication, division, addition, and subtraction, which is what explains the rest of this problem over here. Okay, so go ahead and take a few minutes to complete the few problems, pause the video, and when you're done, go ahead and click play again to continue on. Okay, so let's go ahead and look at the solutions for these. All right, so first one, evaluate the expression 4 minus 2 squared plus 7 minus 3 squared. All right, so we'll start with the parentheses, everything inside the parentheses. And so that's going to be 4 minus 2 first. So 4 minus 2 is 2, so we have 2 squared. Little 2 up top there, plus next set of parentheses is 7 minus 3, which is 4. So we have 4 and then squared because of the little 2 up here. For those of you that don't remember, squaring something just means we are going to multiply that base number with itself. And so when we have 2 squared, that means we're doing 2 times 2. So 2 times 2 is 4, plus our square over here. We have 4 squared, or 4 times 4, which means that's going to be 16. And so now we just have 4 plus 16, which is going to end up being 20. So 20 should be the answer for that first problem. Okay, now let's go to the second one over here. Same kind of thing. We're going to start with that first parenthesis. So we have negative 5 minus 3, that'll be negative 8, all squared. Plus 3 minus 4 will be negative 1, all squared. Now what's cool about squaring stuff is that no matter what, you're going to end up with a positive answer because we all know that a negative number times a negative number will end up being a positive number. So a negative 8 times another negative 8 will be a positive 64, plus negative 1 times a negative 1 is a positive 1. And so in the end, 64 plus 1 will be 65. Okay, cool. Now let's do the next one. Now we have some minus negatives here, so that's the next curveball. So we'll start with our brackets, the outward parentheses here, and we'll see that we have a negative 1 minus a negative 9. Well, remember with minus negatives here, double negatives, all this really means is that we really have negative 1 plus 9, right? Because like a minus negative cancels out to a plus if you want to think about it that way. So really minus negative just becomes a big plus. So we have negative 1 plus 9, which is going to be 8. So 8 squared plus 5 minus 3 is 2 squared. So 8 times 8 again is going to be 64, plus 2 times 2 is 4, and so in the end here we have a whopping 68 as our answer. And then lastly, just another step forward here, we now are going to do 2 sets of double negatives, and so negative 3 minus a negative 4 is going to be negative 3 just plus 4, right? Negative 3 plus 4 is just going to be 1, and then squared, plus we have negative 1 minus a negative 6, so negative 1 plus 6 is going to be 5, and then squared, which equals 1 times 1 is going to be 1, plus 5 times 5 will be 25, and so at the end we have 26 as our answer. Okay? So that is going to be it for the warm-up problems. Go ahead and check your work if you need to, but with that, we're going to move on to the remaining slides for today's lesson. As a reminder, we always are going to have tutoring every day after school, Monday through Thursday, from 3:45 to 5 p.m. in room 100, if you guys are falling behind or need some help. Today is going to be lesson 1, 2, and 1, 3, which, again, the title is up there on the slides. And the learning targets for today, remember, well, the learning targets being the short, simple phrases you can summarize the learning for today with, would be that students can analyze figures to identify points, lines, and intersections of lines. And then learning target 1B, students can find measures of line segments. As we'll see later, measures just means lengths. We can figure out how long certain line segments are. So one of the practical applications you can use with all this stuff is graphical art design or video game design here. We have what I like to call off-brand Pac-Man here, and you see that not only aesthetically do they have points and lines strewn about to actually make the game, but when you do the programming and are programming it, you have to deal with those shapes as well to form the game that you see in front of you. With some of my engineering classes, I can tell you that using points, lines, planes, all that stuff are the foundation for doing a lot of our 3D modeling. So we can print things using 3D printers and model things for our classes and work. So a lot of good practical applications for this material. Okay, so we have a series of slides here that go over a bunch of definitions. What I'm going to do is just take this. We'll take, I'll give you a second to just write all this down first, and we'll start explaining. Okay. We're going to typically use this format for vocabs. We'll just have a word column with, in this case, points, line, intersection, plane, collinear. And then go ahead and take a second to write the definitions down. Pause the video, and then we'll start up with pictures momentarily. Okay, so let's go ahead and do some pictures. So as you see here for a point is going to be just a location. It doesn't have shape or size. So think back to like Google Maps or GPS, right? Whenever you have a GPS, you type in your address to go somewhere, there's always a blue dot where you are and then a blue dot where your location or destination is going to be. And so that blue dot is no accident. That is a point, and that point is specifying exactly where you are and then where your destination is. And so with that, the point, technically has the shape of a circle, right? But what that's really saying is that point is not giving you any kind of information about the shape of where you are at or the shape of your destination. Okay, so if you go into a local grocery store, for instance, with your GPS, that little blue dot has nothing to say about the shape of that grocery store. All it has to say is about where exactly that grocery store is on the map, its location. And that's the same deal with size. It's not telling you how big the grocery store is, it's just telling you where that thing is located. Okay, whenever we do a point, let's see if we can do the copy and paste here. Okay, so for a point, remember, we have just a circle, just like you see on your GPS. So we can just do a little blue circle here. And whenever we have a point, we always denote that with some sort of label, and that label is usually going to be a letter. So this might be something like point A. We'll just draw a little A there. Okay, it could be any sort of letter or marking depending on what you're messing with, but typically we're just going to have a single letter there of your choosing. So let's go back to line for our vocab words. Okay, so line. A line is made up of points and has no thickness or width. There is exactly one line through any 2 points. So all that really means is that there is an infinite amount of points hovering in space, and we can just pick any 2 of them. So we'll say we have a point right here and a point over here. We'll call this point point B, and this point point C, like that. And all that is saying is that between any 2 points, anywhere, a line is going to connect them. Something like that. Okay? And so that's how we define a line. It just has to go through, it's just that distance or length that goes through two different points. And typically with lines, all we want to do is we want to draw that flat surface, and then we want to add our little arrows at the end. Something like that. Okay, because as a lot of you probably remember, those arrows signify that the line goes on forever, ever, and ever, right? So the line goes through both points B and C, but it doesn't stop there. It's going to go on forever and ever in both directions, left and right. When it doesn't, that is called something that we'll discuss a little bit later. Okay, let's go back to intersection. So intersection, whenever you hear the word intersection, you think of cars driving on an intersection, or the word crossing, or anything like that, right? Well, it's basically the same thing in geometry. The definition here is that the intersection of two or more geometric figures, like lines or planes or things like that, is the set of points they have in common. So we might think of, for instance, a road that intersects, or two roads that intersect at a point. In geometry, all that we're trying to emphasize is that we have, let's say, two lines, for instance. That we can draw our little arrows there. And all we're trying to emphasize in geometry is that an intersection is defined at the set of point or points where the two figures, in this case the two lines, are going to intersect. Okay, so there's an intersection of these two lines at exactly this point that we will call point W. Why not? Okay, so that's the emphasis for intersection in geometry. Next is going to be a plane. Plane is one of those figures or one of those concepts that a lot of students kind of start to dip off on. They have sort of a difficult time understanding what it is. A plane is a lot simpler than you think. A plane is quite simply just a flat surface, anything flat. So if you're watching this in your bedroom or maybe in a classroom or homework lab or something, there's planes all around you. The desk or the table you're using is a plane. It's a flat surface. The walls around you, the ceiling, the floor, all of those are planes. Whiteboard, same thing, all a just flat plane. So a plane is a flat surface made up of all points that extends indefinitely in all directions. So we have just infinite amount of points lying around or hanging out in space, and a plane is just going to be defined by the boundary of those points. Planes must have at least three nonlinear points that make up that plane. So far you can think of a point as a single point, a line as 2 points, and then a plane as 3 points. So 1, 2, 3. And when you go to a math textbook, you might see a plane drawn in a series of different ways, but just know that it's any flat surface, so it can be really any shape. But when I look at math books, I typically see planes drawn as sort of like maybe parallelograms like this. If I had better hand drawing. Yeah, well, close enough, right? So we have a plane. It is a flat surface, so it is technically a plane. And so that plane is going to have three what we call nonlinear points. So 1, 2, 3. We'll call those points J and K and L, something like that. And that would work. Nonlinear just means not in the same line. So in other words, can we draw one line that contains all three of these points without curving? And the answer is no, right? We can draw a line through JK or through KL or through JL, but we can't draw a line through all three. So they are nonlinear points. And so those would make up a plane. Okay. Lastly, we have collinear. And collinear is exactly what it sounds. We have the prefix co, that means together, and we have linear, that just means line, right? So it's points that share a line. They're all on the same line. And so we could even go back to our initial BC line up here, and those will be collinear. You could draw another line down here if you want. And you could put something like 3 points on it, or 4 or 5, or whatever you want to do. We can call those x, y, z. And all three of these points would be collinear because, again, they share a line. They are together on a line. Okay, so go ahead and write those down for your examples, and let's go ahead and move on to actual geometry. Okay, so first example from the book here, we are just going to formally write out different ways we can define or label our different figures. We're going to start with a point over here. Okay, so if we take this image, put it over here, okay, we just want to know what ways we can name points, lines, and planes, just like the slide over here is saying. Points, lines, and planes. Let's figure out how we can name these. And so for points, we've already kind of talked about how we label them. We have a dot and we have a letter typically next to them. And so for points, as an example, you can quite literally just call something point Q in the case of our figure over there with our plane, so point Q. And so if you don't have a physical point with a letter next to it, we can just write out the word point and then put the letter next to it, so that's point Q. Another one we can just do is, point T, something like that. We just grab whatever point we see that is visible, and then we can spell it out like this, and that will formally label our figure, our point. Okay, next are lines. Okay, and how we label lines, there's really two main ways we want to deal with lines here. And the first way is we can actually write out line, whatever the name is, like this. Okay. Now, the key here is when we name lines, just like with our definitions, when we were doing those, we saw, we want to pick any two letters. So we don't want something like TRQ or line T. We want to pick any 2 points or 2 letters that are on the line, and we can define it that way. So if we're doing this line right here, we can call it something like line TR. Okay, or you can do something like line TQ or RQ or T or QT, anything like that. Okay, it doesn't matter what order the letters are, just as long as you have 2 letters in a row like that, or not even really in a row, but just that are collinear, then that works. Now, if you don't want to write the word line right there, the other way to really do this is you write the 2 letters, so TR, and then if it's an actual line that goes on forever and ever, we can draw a little symbol on top like this. Okay, and we want to make sure we actually draw the arrows because, again, that is telling us that is going to be an actual line, whereas if we don't do that, we'll later see that we're talking about a line segment usually. Okay, so that is really the first way that we can define a line. We can kind of sandwich those two together as the first way. The second way is by looking at the lines over here, we have letters that are not points, right? We see TRQ, for instance, that are all points on the line, but over here on the far right of that same line, we see just a C floating there at the end, and it does not have a dot, it doesn't have a point, so it's not a point. So that kind of italics or cursive looking C is denoting the entire line. So we can actually just call this line, line C. Just like that. Okay, so we can call this something like line TR or line C. Again, we can call it line C because C is not a point. That's just a label for the overall line. We could not call this line T or line R or line Q because those are actual points on the line. We either have to define a line with 2 points or by the label that they give us on the end there. Okay. So those are the 2 ways. And then lastly, we're going to look at how to label planes. Okay. Now, with points, obviously we just need 1 letter. For lines, we need at least 2 letters. Or with planes, that goes up to 3 letters. So as long as we define a plane with any 3 letters that are nonlinear, then we are in the clear. Okay, so for instance, pick any 3 letters you see on here that encompasses the plane. Well, I can pick S. S is over here, so we'll do S. And then we'll choose T. And then we'll choose something like Q. Okay, and so that is formally how we can name or label a plane. If you want, you can draw the word or write the word plane in front of that, but that's not too big of a deal. But just know if there's 3 letters like this, we're talking about a plane, because lines, we're always talking about 2 letters, and so this could not be a line, and then points are obviously just 1 point. Now, kind of similar to a line, the second way we can deal with planes is we can look for a letter in the corner somewhere that is just referencing the entire plane. And in this case, that's going to be A, this A in the corner down here. We can just call this thing plane A. And that will actually encompass the whole thing. So we don't have to use points as long as we have a short label like that present somewhere on the plane. Okay, so those are the ways that we formally label points, lines, and planes. Okay, so then I'm going to have you do a couple practice problems. Go ahead and take a couple minutes to formally name our objects here, and then pause the video and we'll go over the solutions. Okay, so we're back. Let's look at number 2. Name how many planes are labeled in the figure. Well, we're talking about the whole figure here, by the way, not just one or the other. And so across the entire figure, we have exactly 2 planes, right? We have this plane here and this plane here. If we wanted to name those, it looks like we could name this something like plane R. Down here, we can name it plane Q. Or again, you can pick any 3 nonlinear points to name the planes as well. And then number 4, name the intersection of lines M and T. Okay, well this is line M, right? We have that label here, it's not a point. And we have T, again, not a point, there's no dot, it's just a label. So the intersection, or the crossing point of M and T is going to be point C. So we can quite literally just write out the word point and then C, and that should be sufficient. Okay? There you go. So let's go to the next set of practice here. Go ahead and take a second or a minute to formally name 8, 10, 14, and 18 on this slide. Pause the video, and then we will start to go over after you are done. Okay, so let's look at 8. So we have the roof of the house. So how can we define this roof for the house? Which one of our vocab words is it going to correspond with? And you can see that the roof has, it's just a flat surface, right? It's just a flat surface there. And so we're going to call that a plane. 8 is going to be a plane. Okay, move on to 10. 10 says bridge support beams. So that's going to be the vertical lines coming up and down here, not the actual track itself, the support beams. So when you look at the support beams we're going to call just lines because they're going up and down. Then we go to 14. It says a wall and a floor. Well, if you look around the room you're in right now, you can look at a wall and look at a floor. So you have 2 flat surfaces, and what are they doing? Those 2 flat surfaces, or those 2 planes, are going to intersect. So you can write intersect here, or you can write intersecting planes, you know, whatever you want to do, but that's what those are. And then when we go to number 18, it says a telephone pole. Telephone pole is just going up and down, and so again, that is going to be a line. Okay, with some of these images and descriptions, there's a little bit of variability we can do here with the answers. You know, for instance, with number 10, you can maybe consider these collinear, right? Just depending on how detailed you want to be. So don't feel too bad if you were a little off. Like I understand when I was teaching this in class that some students saw certain details and corresponded the words with those. And as long as you get the concepts, you're good here. So don't worry too much if you got them wrong, as long as what you were picturing was accurate. Okay. All right, so we're about halfway done here. We're going to skip all the way to the vocab. We just have 3 more vocab words and then a couple more examples and we're done. And so there are 3 words. Go ahead and you can add these down below our other vocab words, or you can start new. It's totally fine either way. And so I'll give you a little bit to go ahead and write down the 3 vocab words here: line segments, congruent, and congruent segments, and then with the definitions. So go ahead and pause the video and then we will continue with these. Okay, so let's go ahead and go over the definitions and the pictures. So let's go ahead and copy and paste. Okay, so let's go over the definition for line segment first. Okay, so if you guys have ever heard the word segment before, segment just means a piece or a section, sort of, right? So a line segment is just a segment or piece of a line. Formally, it's defined as a measurable part of a line that consists of 2 points called endpoints and all of the points between them. So what that might look like, for instance, and again, forgive me for non-straight lines here. Let's say we draw something like that. And let's call this, let's see, we have a point here. We'll call that point A. Over here, we'll call this point B. Over here, we'll call this point C. This is going to be line AB or line BC or whatever you want to do. Okay? A line segment is going to be a segment, just a piece of this line between 2 points. So AB, this little piece right here, is considered a line segment. BC is considered a line segment. Everything between A and C is considered a line segment. Okay? Just as long as it is a definitive, measurable length of the line. It's not the component that goes on forever and ever. It's just one of the pieces that you are choosing, whether it's the smaller one like BC or the longer one that is AC. Okay, the 2 points you do choose for your segment, we call those endpoints. So AB, line segment AB, would have endpoints A and B, right? And how we do want to actually formally write these, let's say we wanted to highlight line segment AB, for instance, we would label it as AB, and instead of drawing a line with the arrows on it, we're just going to draw a little line on top. And that actually shows that this is line segment AB because there's no arrows there. Okay, so if you ever see something like this with the little line on top, that means a line segment, not line. Okay. Next we have congruent. And congruent is very, very simple. It just means identical or the same. That's it. So if you have 2 things that are the exact same, they are congruent. And so if we go back to our picture here, you can draw anything. I'll draw 2 triangles that are supposed to be identical to the best of my ability. Okay. And if they are identical, they're of course both the same triangle, and then also they have the same lengths. So we have maybe a 6 here, meaning a 6 here. We have maybe a 7 here, and a 7 here, and then something like a 10 here, and a 10 here. Okay, so these shapes, these 2 triangles, are the exact same thing. They're copy and paste of one another. So we call those congruent. Okay, and the last definition down there is just that, it's congruent segments. So it would be 2 segments, 2 line segments that are identical or congruent. Okay, so maybe something like this, we'll call this line segment F and G, and we'll call this one something like line segment O and P. Okay, and so what I asked my students was, are these 2 line segments congruent? Right? Are they going to be identical let's say the length was 5 units up here and 5 units down here. Would they be identical? And really the answer is yes, because when you go back to the definition, it just says that they have the same measure or the same length. Okay? They don't have to be oriented the same way. One could be kind of curved, one could be straight, or diagonal is what I meant to say. They're just floating in space, but as long as they're the same length, the same measure, then they are going to be identical or congruent. The points don't even matter. It just talks about the length of each of those. So these would be examples of congruent segments. Okay? All right, let's go down to the example here. And we'll get by these, pretty quick, I think, because a lot of you probably know what's going on. But for this first example, we're going to find the measure or find the length of z or xz, line segment xz. All right. Well, we see xy is 11.3, and we see yz is 3.8. And so if we want to find xz, meaning the whole thing, all we're going to do is just add both line segments together, right? So we have 11.3 plus 3.8, and that is going to add up to something like 15.1. And so the measure of xz is just going to be 15.1 centimeters. And that's it, okay? Let's go down to the next one here. So now we want to find the measure of QR. When we look at our figure here, we have line segments PQ, QR, and PR. We know that PQ, this small piece here, is 6 5/8 feet. We know the whole thing is 13 3/4 feet. And so now we just want to know what QR is. We want to know what's left over for the length of this piece. Okay? And so you would just subtract, right? You would just subtract 6 5/8 feet from 13 3/4 feet. And so we can do that real quick just for some practice for fractions. It's a good idea, probably. Okay, so you might remember from fractions that when you are adding them together and subtracting them, that the denominators or the numbers on the bottom have to be the same, right? And so really we want to do 13 3/4 minus 6 5/8, because that is going to get us our answer for QR, right? Subtract those two, we get QR. Okay, so what we do is we want to make sure the denominators are the same. So the easiest way to do that is to multiply this fraction over here by 2, because 4 times 2 is 8, so both fractions will be 8 then. So multiply both of those by 2, and that is going to give us 13 as the base number still, and then 6 over 8 minus 6 and then 5/8. Okay, and then from here we just subtract everything. 13 minus 6 is going to be 7 as our whole number, and then 6 minus 5 is 1, and then we keep the 8's together because they are denominators, so 1 over 8. And that should be the correct answer. Now when I taught this, I had a number of students say, well, don't you multiply the 13 as well by 2 since you're doubling everything? And the answer is no, because when we are doubling the fraction, 3 over 4, all we are is changing how the fraction looks. We're not actually changing the value of the fraction. So for instance, 3 over 4 is just 75%, or when you put it into a calculator, it's 0.75, right? 3 divided by 4 is 0.75. When you go down to 6 over 8 and do the same thing, do 6 divided by 8, you're still going to get 0.75 or 75%. These fractions equal or mean the same thing still. You're just transforming how it looks so it can mesh better with the other fraction. And so 13, you're not really changing anything. You don't have to change the way 13 looks. 13 is good the way it is. But you just had to change the way the 3 over 4 looked in order to get it to be able to subtract with the other fraction. Okay, so we're not really changing the value of anything. We're just kind of changing how it looks. So we don't touch the 13. Okay, cool. Let's go back here. Last couple. Okay, so we have our last kind of problem that we're going to go over here. So we have find the value of x and bc if b is between a and c. AC equals 4x minus 12, AB equals x, and BC equals 2x plus 3. Now, I know what a lot of you are thinking, oh man, word problem, I don't know how to do this. Okay, so whenever we encounter a word problem in geometry, especially in geometry, we almost always want to draw a picture. And so when we do that, this becomes a lot easier. And so let's go ahead and copy this. Go back to Jamboard, and we will paste it. I promise it's not nearly as bad as you think. You just have to read it. So it says find the value of x and b and c if, and here's the key here, if b is between a and c. Okay, well, let's draw that out. B has to be between a and c. So all we're going to do is draw a line segment. Since B is between A and C, we know B has to be in the middle, like this. So B, and then we can draw A and C, like that. Okay, so B is between A and C, so we got that. And then it tells us the rest. So AC, so the length of the whole thing here is going to be 4x minus 12, right? AC is 4x minus 12. So the length of the whole thing is 4x minus 12. All right. It says AB equals x. So this length here between A and B is just going to be x, like that. And then it says BC, the length right here, is going to be 2x plus 3. Okay, so we just want to find the value of x. We'll start with that. Just make it a simple algebra problem. Okay, now, so we know AB is x, we know BC is 2x plus 3, and we know the whole thing is 4x minus 12. And so all we're going to do is set that up. We know that AB plus BC is going to equal AC, right? This piece here plus this piece here equals the whole thing. And so we're going to write that out algebraically. AB, which is x, plus BC, which is 2x plus 3, so plus 2x plus 3, equals the whole thing, which is 4x minus 12, so equals 4x minus 12. Okay, now from here it's just basic algebra. And so we'll go ahead and combine the like terms. We have, we'll combine the x's here. X plus 2x will be 3x plus 3 equals 4x minus 12. Okay, now there are a few different things you can do here that are all correct. We'll start by combining the x's, because that's a little easier. So we will subtract 3x from both sides. So 3x minus 3x is 0, so they cancel out. And then we have 3 equals 4x minus 3x is 1x, or just x, same thing. And then we have minus 12. All right. Lastly, to get x by itself, we want to add 12 to both sides. So in the end, 3 plus 12 is 15, which equals, those cancel out, and we're left with x. So in the end, x equals 15. So that is our answer. It says find the value of x, and x is 15. The other one just says find the actual value of BC. And so BC we know is 2x plus 3, right? Well, it wants us to actually give them a number. So all we're going to do is plug in that x value, right? So we start with 2x plus 3 for BC. We'll plug that 15 in, so we have 2 times 15 plus 3. 2 times 15 is 30, so we have 30 plus 3, and so at the end we have 33 as the answer for BC. So find the value of x, which we found was 15, and then BC, which we found the value to be 33. Okay, and that's the gist on how you do these problems. Just draw out the picture, label everything, and then do some algebra. So with that, go ahead and try problems 10 and 16, and that should be sufficient. Okay, go ahead and take a few minutes, pause the video, and then unpause the video when you want to check your work. Okay, so let's go ahead and finish this up for 10 and 16. Very similar directions as the problems we were just doing. Go back here. Okay, so word problem, right? We want to draw a picture. So find the value of the variable. Variable just means letter, right? So like in this case, it'll be C. Find the variable, the value of the variable and yz if y is between x and z. Well, all right, so we'll draw a picture out. We know y has to be between x and z, so y is right here. So we have x and then z. All right, now let's just draw everything out for number 10. We'll start with number 10. So xy we know is 11. We know that xz, so the entire thing, is going to be 83. And then we know yz is 4c, so this part's going to be 4c. Okay. Well, just like last time, we know that this piece here, xy, plus this piece here, yz, is obviously going to equal the whole thing, right? This plus this makes up the whole thing. So we're just going to write that out algebraically. So we have 11 plus 4c equals 83. Well, we'll go ahead and combine the like terms. So we'll subtract 11 from both sides, like that. 11's cancel out, and we're left with 4c equals 72. And then lastly, we divide both sides by 4. And we're going to have c equals 72 divided by 4 is going to be 18, I believe. Okay, so c is 18. So we found the value of the variable. So in this case, it's going to be 18. Okay, 18. And then now we need to find yz. Yz was 4c, right? Yz was 4c. So 4c then becomes 4 times c, which is 18. And so we know 4 times 18 is 72. And so 72 is going to be correct answer here. Okay. So for 10, it's going to be c equals 18 and yz equals 72. Okay. Now let's go ahead and do 16. So we'll go ahead and draw a picture just like last time, where we have y in the middle, we have x, and we have z. And then it says xy is 11d. It says yz is 9d minus 2. Then it says xz, so the whole thing, is going to be 5d plus 28. And then we'll go ahead and just add everything together like last time. So we have 11d plus 9d minus 2 equals 5d plus 28. And then from here, we'll just combine like terms like normal. 11d plus 9d will be 20d minus 2 equals 5d plus 28. Okay. We'll go ahead and combine the d's now. So minus 5d minus 5d. Okay. 20d minus 5d is 15d minus 2, which equals 28. Okay. Now we want to add the 2 to both sides to get rid of that minus 2. So plus 2 plus 2. So we have 15d equals 30. And then lastly, we divide both sides by 15 to get that d by itself. And so in the end, d is going to equal 30 divided by 15 is 2. So d is going to be 2. Now we do need to find yz, so we just plug that right back in. Yz is going to be 9d minus 2, right? Well, we'll just plug that in real quick. 9 times 2 minus 2. 9 times 2 is 18, and then minus 2. So in the end, yz is going to equal 16. And that's going to be it. Okay, so for 16, the variable d equals 2, and then the length of line segment yz is going to be 16. And that should be all good. Okay. So with that, the homework for this lesson, when you go to the textbook, should be problems 1, 3, 7, 9, 11, 13, and 33 under lesson 1, 2. And then under lesson 1, 3, it should be 1, 3, 11, 17, 29, and 33. Remember, these solutions are in the back of the book, so when you want to check your work, you can check your work that way. And remember to email your teacher or go to tutoring if you need any help after that, okay? That's where I'm going to end the video. Stay safe. See you later.